Hello everyone, I am Rasool Ahmad, a postdoc in Micro and Nanomechanics group under Professor Vesai at Stanford University. So in this presentation, I am going to talk about how we can use hierarchical homogenization method to obtain homogenized elastic moduli of large images. So here to start with, here is a basic workflow of digital rock physics. So we start with the grayscale image that we obtain from micro CT scan. And then we segment it into different constitutive materials. We perform a physical simulation on the segmented image, and then we obtain our desired properties. So what is the challenge here? So we know that in order to obtain accurate properties, we need high resolution and large field of view. So, but that two conditions will result in very large digital images, and it will be very costly to perform some physical simulations on those images. So here we are going to talk about a method that namely hierarchical homogenization method that will enable us to run simulations on these large images. So here is the outline of this talk. So first I will describe the basic idea behind the hierarchical homogenization method, or HHM. Then because hierarchical homogenization method is an approximate method, so it will inevitably introduce some error. So I will talk about how we can characterize and then control this error to apply this method with confidence. And then how we can reduce this error by introducing the concept of padding. So here is the basic idea behind the hierarchical homogenization method. So we have a large image of size capital N, and which has two faces, black and white. So what we do, we partition this big image into small sub-images of size small n, and then we homogenize these small sub-images individually using GeoDict. And then we assemble these homogenized sub-images into this intermediate image of size capital N by small n, and that assembled image will preserve the spatial distribution of the properties. And then we again perform homogenization of this intermediate image, and we obtain our final homogenized property. So in this way, it will obviate the need for solving this full image of size capital N, which can be very expensive. So here how we perform the homogenization of the sub-images. So say we want to homogenize this sub-image of size small n, which is represented here in the red region. We extract this image, extract this sub-image, and then we apply periodic boundary conditions and solve this elasticity equation. And we just obtain the homogenized properties from the equilibrium elastic fields, right? So these are the microstructures of the 5 rocks that we use in this study. So these are sandstones of size 900 by 900 by 900. So we have 2 Beria formation rocks, 1 Castlegate and 2 Fontainebleau. So we segment these 5 rocks into two materials. So phase 1 red, which is mineral, and we assign the properties of quartz. So bulk modulus is 36 and shear modulus is 45 GPa. And the second phase is the pore. So the bulk and the shear moduli are 0. So how do we estimate error? So for that, we need the true homogenized value, which we obtain by running direct numerical simulation on the original big image of size 900. And that's our ground truth, or the true value. And then we perform hierarchical homogenization method. We obtain the value. So we subtract this true value from the HHM value to obtain the error. And we study the variation of error as a function of this sub-image size n, which will vary from 75 to 300. The big image is of size 900. So here is the result. So error variation in B1 microstructure. So here I am plotting error in bulk modulus and shear modulus as a function of subimage size small n. So HHM value is given here in blue data for both bulk and shear modulus, and I am fitting this data with this functional form m infinity plus c into n to the power minus 1. So we see it fits very well. So the first observation is that HHM moduli follow a power law with fixed exponent of minus 1 with respect to subimage size n. This is the power law. And these two, m infinity and c, are fitting parameters. And m infinity is the asymptotic value of the homogenized modulus of this large image, right? N tends to infinity. So we see that this kind of behavior holds across all 5 microstructures. So for all microstructures, HHM bulk modulus and shear modulus follow this moduli follow this power law with fixed exponent of minus 1. So now we see that we can use this power law to estimate the homogenized elastic moduli of large images. So we can perform hierarchical homogenization for different subimage size, and we can fit the data with this power law. We can obtain m infinity. So here I'm showing the result for all the 5 rocks. So M900 is the ground truth obtained by performing direct numerical simulation, and M infinity is obtained from this fitting procedure. So we see for both shear modulus and bulk modulus, there's ground truth, and the HHM value agrees quite well with each other, right? So now how we can reduce error even further. So we wanted to homogenize this red region. So instead of extracting just this red region, we introduce some padding material. So now we extract this larger image of larger blue image. So now we apply periodic boundary condition on this larger image, but only we obtain, but after solving the elasticity equation, we homogenize the elastic fields inside this red region to obtain the homogenized property of this red subimage that we were interested in. So this extra padding will somewhat mitigate the effects of periodic boundary condition, and it will also account for the effect of surrounding materials in the homogenized properties of these subimages, right? So here is the result. So the effect of padding in B1 microstructure, here again I am showing the variation of error as a function of subimage size, and different color represents different padding thickness. So the blue is for no padding, orange is for padding thickness of 10, which means that we have extra 10 voxels in each direction, and green is for padding thickness of 20. So first observation is that for fixed subimage size, error decreases as we increase padding thickness. And across all padding thicknesses, the hierarchically homogenized moduli still follow this power law scaling with the fixed exponent of minus 1. And these are the fitting parameters. So we see that for all padding thicknesses, the m infinity, which is the asymptotic value, they remain almost constant for both bulk modulus and shear modulus. So the value of C is changing, which means that faster convergence as we increase the padding thickness. So we observe this kind of behavior across all 5 microstructures that we have, that error is decreasing with increasing padding thickness, and this power law behavior is followed for all padding thicknesses across the 5 microstructures. So to conclude this talk, we saw that this hierarchical homogenization approach, it can provide a reasonably accurate estimate of the homogenized elastic moduli of large image. And in this way we can, and we also see that using in this method, we don't need to solve this full large image. And the hierarchically homogenized moduli follow a power law behavior with a fixed exponent of -1 with respect to subimage size. And then we can exploit this power law scaling to obtain this fitting parameter m infinity, and this m infinity is a good approximation for the true value. And we saw that we can reduce this error by introducing some extra padding material that will account for the surrounding around the subimages. So with that, I want to thanks for your attention. So if you are interested and go into details, so we have submitted this paper and is still in review in JMPS. But if you like, you can access this archive preprint. Thank you very much.